Okay, so now we're going to do discussion 9.2, electrochemistry. I just want to warn you, this is going to be a long one, and this is actually a pretty tough topic, so a lot of practice on your part will be required. Alright, so first I want you to think about different types of energy. Right? Energy comes in all sorts of different forms. It comes in electrical, thermal, kinetic, potential, mechanical, electrical, chemical, etc. So I want you to think about the types of energy used for these different things. What type of energy makes a car run, and how is gold or silver plated onto a necklace or something? Okay, so cars run on chemical energy because the bonds in gasoline are broken and then reformed, and that's how the energy is produced. But electroplating works with electrical energy because it's caused by the transfer of electrons from one species to another. And those two forms of energy are what we're going to focus on in this discussion. Alright, so we're going to look at two types of electrochemical cells. A voltaic cell is a device that converts chemical energy into electrical energy via a spontaneous reaction. And an electrolytic cell is a device that uses electricity to force a non-spontaneous reaction to occur, in turn creating chemical energy. Alright, so in both of these cells, the reactions we're looking at are redox reactions. And the two types of cells are opposites of each other. And if you look at the definitions, you can see that. Voltaic converts chemical energy into electrical with a spontaneous reaction. And an electrolytic uses electrical energy to create chemical energy with a non-spontaneous reaction. So let's define a couple terms, and we'll dive into the cells. So an electrode is the site of oxidation and reduction in an electrochemical cell. Now the anode is the electrode where oxidation occurs, and the cathode is the electrode where reduction occurs. And you can remember that by saying red cat, anox. Reduction occurs at the cathode, and oxidation occurs at the anode. Red cat, anox. And it's important to note that even though the voltaic and electrolytic cells are opposites of each other, this truth will always hold true. Reduction always occurs at the cathode, and oxidation always occurs at the anode. So again, in a voltaic cell, a spontaneously occurring redox reaction, electrons are transferred. Now, we can separate the two half reactions that are occurring in two different vessels and force the electrons to travel through a wire. Right? Once we do that, we can harness the electricity. And this is actually how batteries work. Batteries, are voltaic cells. So here we have a diagram of a voltaic cell. And I'm actually going to leave this program and actually draw it for you on my new document camera. Okay, so a voltaic cell consists of two different vessels. And those two vessels will each have an electrode in them and a device connecting the two cells called a salt bridge. Right? The two electrodes will be attached to a voltmeter, okay? And each beaker will contain an electrolyte or an aqueous solution. Okay, so the first cell we'll call the anode, and the anode is usually written on the left. And the anode in the voltaic cell is the negative electrode. So the other cell we'll call the cathode, and that will be the positive electrode. Now what we're going to do here is look at the reaction between zinc and aqueous copper 2 sulfate. And in that reaction we're going to form solid copper and zinc sulfate. Right now if we look at this reaction and all the oxidation states of the elements, we see that in this equation zinc is being oxidized. Since oxidation occurs at the anode, let's see if I can zoom out a little bit here. I can't, so let me just adjust this and put it up a little bit higher so we can see everything on the page. Sorry, I'm gotta get used to this thing. Okay. So since oxidation occurs at the anode, the electrode in the anode will be made out of solid zinc. And so the electrode at the cathode will be made out of solid copper. Now what's occurring at the anode is zinc atoms are being oxidized into zinc ions. Now because that's true, the electrolyte at the anode would be a solution of zinc sulfate. So we'll have additional zinc ions and sulfate ions floating around in there. Right? Now reduction occurs at the cathode, so we'll need some copper ions in that solution in order to be reduced. So we'll have a solution of copper sulfate at the cathode, excuse me. Now the device connecting the two is called a salt bridge. And we'll explain the function of the salt bridge in a second. So because zinc is being oxidized into zinc ions at the anode, electrons are being freed up from zinc. Right? Now because copper ions are being reduced at the cathode, that is creating that positive charge on the cathode. Because we have electrons at the anode and a positively charged cathode, the electrons will be drawn through the wire from one cell into the other. And they'll always travel from anode to cathode because the electrons are always being freed up at the anode because that is where oxidation is occurring. Now, the salt bridge, its purpose is to help ions migrate into either of the cells. And the reason ions need to migrate is because the charges of these cells are constantly changing as the process occurs. Okay? So as electrons leave the anode will become more positive. Right? So the salt bridge will have some kind of salt in it that'll contain ions. Now I'm writing potassium chloride ions because usually salt bridge contains something like potassium chloride. You want to make sure that the ions in the salt bridge don't interfere with what's occurring in the cell. So as the anode becomes more positive, the chloride ions will flow into the solution, neutralizing the charge. And as the copper ions are reduced, the cathode will become more negative, so positive ions will flow into the cathode. So that's the purpose of the salt bridge. Now, one thing I want to reiterate, whatever metal is more reactive will always go at the anode. And the things you want to be able to label in here are the electrodes, which one is the cathode and the anode, plus their charges. Right? You want to label the ions in solution, the salt bridge, and the voltmeter. Okay, so moving right along. Now, how can we determine which metal, which element will be more reactive? Well, here we have two equations, copper reacting with aluminum chloride and aluminum reacting with copper 2 chloride. Now, when we combine copper with aluminum chloride, nothing happens. And that is because aluminum is more reactive than copper. So if we try to react aluminum with copper 2 chloride, we'll get a reaction, a single replacement, which will produce copper and aluminum chloride. Now, we determine the relative reactivity of metals by looking at the activity series of metals. Now, we saw this when we were in Chem 1 as well. Now, elements that are higher than others on the activity series will be more reactive than them. So potassium is more reactive than sodium, and sodium is more reactive than zinc. So if we look at our last example with aluminum and copper, here we see aluminum and here we see copper. Now, copper would not react with aluminum because aluminum is higher than copper on the activity series. Right? If magnesium were going to react with aluminum, then you would see a reaction. And what we have on the left here is a table of standard reduction potentials, and those are measured in volts. Now, the standard reduction potential is the amount of energy released or required for those reduction reactions to occur. And they're all based on the reduction of hydrogen ions. You see that hydrogen ions have a cell potential, electrode potential, of 0. So all these values are based on what is known as a standard hydrogen electrode. And here is the standard hydrogen electrode. Okay, so first of all, these values can be found in table 24 of the data booklet. Those and a whole bunch of others. Right? And here's a standard hydrogen electrode. What you have is a tube containing hydrogen gas at 1 atmosphere of pressure. Right? The hydrogen gas, the tube is connected to a platinum electrode. And everything is submerged in 1 molar acid solution. So that is 1 molar strong acid. So we have 1 mole of hydrogen ions per liter. All right. So those are things you have to know about the standard hydrogen electrode. You have to know hydrogen gas at 1 atmosphere, platinum electrode, all submerged in a 1 molar acid solution. And you also have to know that the standard cell potentials on table 24 are a comparison of the potential compared to hydrogen. All right, so line notation. Line notation is a simplified way of showing the reactions taking place in a voltaic cell. To do this, we're going to show the oxidation process, and we're going to separate the products and reactants with a single vertical line. We'll then use a double vertical line to separate the 2 cells, and the double vertical line essentially represents the salt bridge. Then we're going to do the same thing for the reduction process that we did for oxidation, so separate the reactants and products with a single vertical line. So for the reaction we did in our sample voltaic cell, it would look like this. We started by oxidizing zinc ions. So we separate zinc and the zinc ion with a single line. Then the electrons traveled over to the anode, so we'll draw a double line to separate the 2 half reactions. At the anode, copper 2 ions were being reduced to copper. So this is just another way of showing that reaction and what's actually happening there. All right, so calculating cell voltage or cell potential. So the values we see in the data booklet are just values for the electrode potentials for the individual species, whether they be atoms or ions. Right? So to find the overall voltage for a cell, right, we're going to basically add the values we see in table 24. However, if the reaction you see in table 24 is reversed, we're going to use the opposite value of the voltage. And once we do that, we'll just add the voltages together to obtain the overall cell voltage. So in this example, we'll pull out the oxidation half reaction. We see that lead is reacting with lead 2. And I record that cell potential as 0.13 volts. Well, if I look at my table 24 here, and I find lead down here, I see that we are having lead 2 being reduced to lead, and it's negative 0.13. But since we are showing lead being oxidized, we will reverse that value, and it will be 0.13 volts. And then we have copper 2 going over to copper, and the value in the data booklet is 0.34. So once you have those values, you add them together, and you get that the overall cell potential is 0.47 volts. Okay, so now we're going to do some practice calculating cell potential. All right, so we see nickel being oxidized into nickel 2. So we'll look in table 24 for the reduction potential of that and reverse the sign because it's oxidation. And we'll add that to the reduction potential for copper 2 to copper. And when you add those together, you should get 0.6 volts. All right, this next one shows iron being oxidized into iron 3. Now, if you look at the data booklet, you will not see the reduction potential for iron to iron 3. You'll see iron 3 to iron 2, and then iron 2 to iron. All right, so when we do this, I don't think you're going to have to do it for the IB, but you have to take into account the stoichiometry of each the removal of each electron. And I can show it to you in class, but I'm not going to bother showing it to you here because it'll take too much time. So we just have to know that that reduction potential is negative 0.04. So the oxidation potential will be positive 0.04. And again, we have copper 2 going to copper. So when we add those two together, we get 0.38 volts. All right, so try this next one on your own and see if you can work it out. All right, so this is showing line notation. So we see lithium is being oxidized into lithium ions. And we have silver ions being reduced into silver. So we're going to find the reduction potential for lithium ions to lithium and then reverse the sign. And then add that to the reduction potential for silver to ions to silver. We get positive 3.84 volts. Finally, we have what happens in the electrolysis of water. So when we electrolyze water, as you'll see, we're going to both reduce and oxidize. We're going to reduce the hydrogen to produce hydrogen gas and oxidize the oxygen to produce oxygen gas. So
So that happens in 2 steps, as we can see below. Now, both of these steps, individual steps, can be found in the data booklet. Now, for oxygen, since it's being reduced, we're going to find water being oxidized and reverse the sign. Now, for water being reduced, we see that we only have 1 electron in that reduction reaction. So we're going to have to take the value we see in the data booklet and reverse it. Or, and double it. So when we do that, we should get negative 2.89 volts. Okay, so we can also relate cell potential to Gibbs free energy and spontaneity. Here's an example question. It says, for the following reaction, calculate the cell potential and the change in free energy of the reaction. Using your answers, state whether the reaction is spontaneous as written and explain. So to do that, we're going to use this equation. The Gibbs free energy is equal to the negative number of moles of electrons transferred, that's N, times F times E. Now, F is Faraday's constant. It's 9.65 times 10 to the 4th coulombs per mole. Now, both the equation and Faraday's constant can be found in Table 1 of the data booklet. So, E is the cell potential for the process. So here we have our famous reaction of copper 2 going to copper and zinc going over to zinc 2. So we have to calculate the cell potential like we did on the previous slide, and we get the cell potential to be positive 1.10 volts. Alright, so when we plug into the equation, we get negative 2. Now, the reason I put in 2 for the number of moles, if you break that reaction into its 2 half equation, you'll see that 2 moles of electrons are transferred from zinc to copper. So we get negative 2 times Faraday constant times the cell potential, and we get negative 2.1 times 10 to the 6 joules. Alright, so we can say that this process is spontaneous because delta G is negative. Right? Now, it's important to note here that if you have a positive cell potential, then the reaction will always be spontaneous because we have that negative sign in the equation. So if we're multiplying by a positive cell potential, the answer will always be negative. And if the cell potential is negative, then delta G will always be positive and therefore non-spontaneous. For those of you wondering about how we come out with the unit of joules, well, we're going to take the number of moles of electrons, multiply by Faraday constant, which is coulombs per mole. When we do that, moles will cancel, and we'll be left with just coulombs. Now, a volt, the complex unit for a volt is actually joules per coulomb. So when we multiply by the number of volts, the coulombs will cancel, and we'll just get an answer of joules. Now, this relationship between cell potential and delta G can be illustrated with example number 4, where we show water being broken up into hydrogen and oxygen. We see the cell potential for that process is negative. That tells us that this is a non-spontaneous process. And that makes a lot of sense, because if it were, water would then spontaneously break apart into hydrogen and oxygen gas, and we know that that does not happen.
So, reactivity series for metals. So for metals, a more reactive metal, one that is higher on the series, will have a tendency to lose electrons. That means the higher up they are, the more likely they are to be oxidized. So sodium is more likely to lose electrons than copper because it has a lower ionization energy. Okay? So the more reactive a metal is, the higher on the activity series will be, and the higher its tendency to be oxidized. So the higher on the reactivity series is, the better it is as a reducing agent. Now for nonmetals, the more reactive nonmetal will have a tendency to gain electrons. So fluorine is more likely to gain because it has a higher electronegativity than, well, anything. So the more reactive a nonmetal is, the higher on the activity series it will be, and the higher its tendency to be reduced. Right? Now, the higher the nonmetal is on the reactivity series, the better it is as an oxidizing agent. Okay, so let's do a little practice. We have 3 reactions here, and it wants us to use the results of those reactions to determine an activity series for those metals. All right, so let's go ahead and look at each individual reaction. So I see the first one, cadmium is reacting with nickel ions and forming cadmium ions. Because that's true, we can infer that cadmium is more reactive than nickel. In the next one, we see nickel reacting with silver ions to produce nickel ions and silver. So we can say that nickel is more reactive than silver. Finally, we have zinc reacting with cadmium ions to form zinc ions and cadmium, so we can say that zinc is more reactive than cadmium. So if we're going to arrange them in decreasing reactivity, we want the most reactive first. And I see that zinc is greater than cadmium, and cadmium is greater than nickel, and nickel is greater than silver, so that tells me that zinc must be the most reactive. Now, cadmium is greater than nickel, and nickel is greater than silver, so cadmium must be greater than nickel, and nickel we know is greater than silver, so this is our order. Right? That makes zinc the best reducing agent because it is highest in the activity series as determined from that exercise. And silver will be the best oxidizing agent because it is the lowest in the activity series. All right, so now let's talk about electrolytic cells. So an electrolytic cell is used to force a non-spontaneous reaction to occur. So in this type of cell, we're converting electrical energy into chemical energy. And what I want you to put right down here is just the general image of an electrolytic cell. So an electrolytic cell, unlike a voltaic cell, will consist of only one reaction vessel. And both electrodes will be in the same vessel. Right? And now, the two electrodes, instead of being connected by a voltmeter, will instead be connected by a battery. And we know that a battery has a negative end and a positive end. All right. The electrodes, again, will be submerged in an electrolyte. Right? We don't really know what that electrolyte necessarily is. We'll see it can be a bunch of different things. Right? Now, what happens in the battery is we have the negative pole, and the negative pole is negative because all of the electrons in that battery are on that side. Now, they want desperately to get to the positive side of the battery. That's all they want to do, but they're blocked inside the battery from doing so. Now, once you connect the battery to the electrodes submerged in an electrolyte, the electrons will travel from the negative pole into this electrode. That will impart a negative charge on that electrode. And the electrons will travel through the external circuit, or the electrolyte, and travel up into the positive side of the battery. Okay, so let's assume we have some positive ions and some negative ions in here. So we'll call that X plus and Y negative. Oh, and that will give a positive charge to that electrode. All right, so what's going to occur, because we put a negative charge on this electrode, the positive ions will migrate over to it and become reduced. So because reduction is occurring there, we know that this will be called the cathode. Now, the positive electrode will attract the negative ions where they will be oxidized. So because they are oxidized, this is called the anode. And this is why I refer to the electrolytic cell as the bizarro world. Because in the real world, we know that things that begin with cat are positive and things that begin with an are negative. But in the bizarro world of the electrolytic cell, our cathode is actually the negative electrode and the anode is the positive electrode. All right, so that's one way I like to remember that, is that if we remember that the voltaic cell is the real world where things labeled cat are positive and an labeled negative, then we can infer that in the bizarro world the opposite is true. But again, reduction still occurs at the cathode and oxidation still occurs at the anode. Okay, so there's a number of different things we can do with an electrolytic cell, but first let's look at the differences between the two. So in the voltaic cell, oxidation occurs at the anode, and the anode is negative, like anion. And reduction occurs at the cathode, and the electrode is positive, like a cation. But in the bizarro world of the electrolytic cell, oxidation still occurs at the anode, but the anode is positive. And reduction still occurs at the cathode, but the cathode is negative. All right, so what can we use electrolytic cells for? We can use them for rechargeable batteries, and we'll talk extensively about that in our option. We can use them to isolate pure elements from compounds, and we can use them for electroplating. So let's first look at electroplating. I'm actually going to draw another picture here. But you can see our electrolytic cell is one vessel with two electrodes in it connected to a battery. Okay, so let's say I want to plate copper on a metal coin. Now, the metal coin will be one of my electrodes, and the other electrode will be made out of copper. And both electrodes will be attached to a battery. All right, now we're going to submerge both of the electrodes if I want to plate copper in some kind of copper solution. So let's just say copper sulfate. Okay, now if we want to reduce these copper ions into copper, we have to attract them to the negative electrode. And if we want them to be plated onto our coin, then we have to make the negative electrode the one attached to the coin. Right? So once we do that, the copper ions will migrate over to the coin and be reduced into copper metal. So that half equation will look like this. Right? Now at the this confuses me. At the anode, we know oxidation is going to occur. So at the anode, copper metal will produce more copper ions and keep the solution filled with copper ions. Right? Now, what you're going to see over time is the size of that copper electrode decrease because the copper in it is being converted into copper ions. So what's happening there is copper metal is being converted into copper 2 ions. Right? And that's how electroplating works with an electrolytic cell. Okay, so there's a number of different factors that can affect the amount of metal that's electroplated. One is the amount of current supplied by the power source. Current is just, it's defined as coulombs per second, and coulomb is a unit of energy. So the faster the current, the faster the rate of flow of electricity. So the more current you have, the more metal will be plated over a period of time. Now, the charge of the ions being reduced, the greater the oxidation state, the greater the number of electrons required to reduce. Right? So every mole of copper 1 ions would need 1 mole of electrons to be reduced, but every mole of copper 2 ions would need 2 moles of electrons in order to be reduced. So the lower the charge, the faster the metal will be plated. And finally, the concentration of the solution. The more concentrated the solution is, the more ions are available, and also the better the current will flow through the solution. So you'll produce more ions that way. Now there's other factors at play as well. Temperature is a factor in the amount of metal, and as Ronak can tell you, that's what his IA was, as well as the surface area of the electrode or the identity of the electrode. Okay, so now let's talk about electrolysis. Electrolysis means separating with electricity. All right, so we're going to look at the electrolysis of a few different things: a molten salt, water, and aqueous solutions. We're going to look at 2 different solutions of sodium chloride, dilute and concentrated, and the electrolysis of copper 2 sulfate. And copper 2 sulfate we're not going to go over here, but we'll talk about it in class. Okay, so let's diagram the electrolysis of molten sodium chloride. So molten sodium chloride means melted sodium chloride. You heat it up so much that it turns into a liquid. Now, in the electrolysis, we're going to use an electrolytic cell. So we'll draw our standard electrolytic cell connected by a battery. That means that here we're going to have our negative electrode, and here we'll have our positive electrode. The electrodes follow the charge of the battery. Okay. Now, the electrolyte in this case is going to be liquid, sodium chloride. Now, what that consists of is liquid sodium ions and liquid chloride ions. Now, once we attach the battery, we're going to electrify those electrodes. Now, because the sodium ions are positive, they will migrate toward the negative electrode and be reduced, right? So that is why we have reduction happening there, and we call the negative electrode the cathode. And so at that electrode, we're going to start with aqueous sodium ions, and those aqueous sodium ions are going to be converted into sodium by gaining 1 mole of electrons per mole of sodium ions. Now the chloride ions will migrate over to the positive electrode. So at the anode, we're going to have chloride ions. I shouldn't have said aqueous there, it should be liquid, I'm sorry. Right, and they are going to form diatomic chlorine. So let's go ahead and balance that by adding our electrons. All right, so this is what is occurring. We have sodium ions being reduced to sodium, and chloride ions being oxidized into chlorine. Now we see that it takes chlorine 2 moles of electrons to be oxidized, and 1 mole of electrons for sodium. So we could say that sodium will be produced at twice the rate as chlorine, because the current is flowing the same over both of the electrodes, and since it takes half the amount of electrons to reduce the sodium, we'll produce sodium at twice the rate. So here on the next slide is a little practice for you to do. Deduce the reactions at the anode and the cathode for the electrolysis of molten silver iodide. Remember, the starting point will be the ions, so you first have to determine which species will be oxidized and which will be reduced, and just write the half reaction. So go ahead and do that. Okay, so we have silver iodide. Once we melt it, it becomes liquid, right? And that means that we have silver ions and iodide ions. Now, we know that we're going to produce pure metals here, or pure elements, I should say. So that means silver ions will be reduced into silver. And to do that, we're going to have to add 1 mole of electrons per every mole of silver ions. And iodide ions are going to be oxidized into elemental iodine. Right? It's always going to be ion over to metal. And you don't necessarily have to draw the cell to visualize this once you get used to it. Okay? So we'll balance iodine and then balance electrons. So my question for you now is, which of these will be produced at a faster rate? Right, and the answer is silver, because silver will only require 1 mole of electrons, while iodine requires 2. Okay, so now electrolysis of aqueous solutions. Alright, so when you've got a solution, what you've got is a solute and a solvent. Okay, now the solvent or the solute could be oxidized or reduced. Right? So the reactions that are occurring at the anode and the cathode will depend on the relative reduction potentials of the solute and the solvent. Right? The substance produced at the cathode will depend on the species that has a more positive reduction potential. Because reduction happens at the cathode, the things that are lowest in the electrode potentials will be the best at being reduced. And the substance produced at the anode will depend on the species that has the lower or more negative reduction potential. So let's look at some examples. Let's first look at dilute sodium chloride. Alright, so let's draw our cell. In that cell, we will have a pair of electrodes connected with a battery, and we will have sodium ions and chloride ions. But what you don't see in there is the solvent, which is water. Right? So we know that we're going to have our cathode and our anode. Now, we could either reduce sodium or water at the cathode. But if you look in your data booklet, or my data booklet, bam, oops. we see the reduction of water is up here with an electrode potential of negative 0.83. Okay? And the reduction of sodium is up here at negative 2.71. That means that sodium is more likely to be oxidized and water is more likely to be reduced. So in the competition for reduction, water wins. And water will be reduced to form hydrogen gas. Okay? So that means we have to balance. Why did I write the 2 up there? Boom. Okay, so that is the process we have occurring at the anode. Now at the cathode, excuse me. Now at the anode, we could either oxidize chlorine or oxidize water. Okay, so now we have to look and see which is better, chlorine or water. So here's chlorine way down here. Chlorine is pretty good at being reduced, not so good at being oxidized. And here we have water, where is it? Right here, above it at 1.23, which is better at being oxidized. So again, water will win the oxidation challenge. And when water is oxidized, you'll produce oxygen and hydrogen ions. And that will be your equation. Okay. All right. So when the products of electrolysis of dilute sodium chloride will produce hydrogen and oxygen at the 2 electrodes. Okay. Now we're going to look at the electrolysis of brine. Now when we say brine, we're talking about concentrated sodium chloride. All right. So when we electrolyze brine, the species produced at the cathode is still hydrogen gas, right? Because hydrogen or water, excuse me, being reduced is still way above chloride, or being oxidized, excuse me, is way above chlorine chloride being oxidized. So hydrogen will still win out. But we see that in the concentrated sodium chloride solution, instead of oxygen being produced at the anode, chlorine gas is instead produced. Right? Now this happens, again, if you look at table 24, you'll see that water forming oxygen and chloride forming chlorine are very close to each other in the table. Now when we make that solution concentrated, that means more current can flow through the solution and it produces something called an overvoltage. And that actually messes up the values. And when you have an overvoltage, the oxidation potential of chloride actually jumps up above the oxidation potential of water. Okay, so instead of oxygen being formed at the anode, chlorine will be produced. Excuse me. Okay. So we don't produce sodium metal again. Actually, I already explained that. I'm just going to move on. Sorry, we're already almost at 40 minutes on this video, so I'm not going to stop. All right, and finally, the electrolysis of water. Now, to electrolyze water, we have to make the water. We have to make it so that it's an electrolyte, right? So what we're going to do is add a little bit of sulfuric acid. Now you can also add salt, but industrial electrolysis they use sulfuric acid because it's a more effective electrolyte. So when we electrolyze water, we're going to produce oxygen at the anode according to that equation, and we're going to produce water at the cathode. And actually that is the error. I knew I made an error. I knew I made an error on this equation when I did this before. I don't know if you could tell me that I was pausing, but I put the electrons on the wrong side. Okay. And finally, finally nothing. That's it. So this is officially the longest video by far. Please bring any questions you have to class, and we'll talk about the electrolysis of a copper sulfate solution when we get there. But after going through this discussion, I'd kind of like you to try that all on your own. All right. Well, thanks for watching.